Find equivalent mass and stiffness of the system shown in figure. This is a drum which is connected to a spring. The drum has the radius r, mass m. The moment of inertia of the drum is id. Assume that the drum will have a translational motion in the x direction, and this drum is connected to a pulley. The pulley is mounted on a slope and then a mass of 2m is hanging on the pulley. Pulley has moment of inertia equals to ip. This mass is supported with a spring of stiffness 2k, which is connected to the ground. The inner radius of the pulley is rp, and the outer radius is 2rp. So what we want to do in this is we want to find the equivalent mass and equivalent stiffness of this problem. We are going to use energy method to solve this problem. So we will first find the equation for potential energy through which we will find the equivalent stiffness, and then we will find the kinetic energy through which we will find the mass, equivalent mass. Okay, so let's proceed with our potential energy. So the potential energy V can be written as equals to half kx square, where x is the translational motion of this pulley and the potential energy stored in this spring, okay, plus half 2k y square. So the motion of this is in y direction, this is y direction, okay. The spring will have a motion in the y direction. Its stiffness is equals to 2k. So there's one more thing. We need to first find every coordinate or every motion in terms of x. So if you look at y, or if you look at, let's do the theta first. So this is the motion of the pulley, which is in theta direction. Theta times rp is equals to x. So theta can be written as x over rp. This is one relationship between x and theta. You can also find y, which is downward displacement. Y equals to 2rp times theta. Okay, so y is the string that is, or the rope pulley, which is connected to 2rp diameter pulley. So this is 2rp times theta. Now you can find y in terms of x very simply multiplying this by 2. Okay, so let's find v now. V is then equals to half kx square plus half times 2k times y square. So y can be equals to 2x, okay, and that is equals to 2x square. So this is then equals to half 9k x square. Okay, so that's what we have done. This whole thing you can represent as x, so you can write y equals to 2x, and this 2x we have used over here. Okay, so the equivalent stiffness is this term over here, that is 9k. So the equivalent stiffness of the system of springs is equals to 9k. Now let us find the equivalent mass of the system. Using the same logic, we'll first find the kinetic energy of the system. So the kinetic energy is equals to the translational energy. Translation energy is in terms of mass and translational degrees of freedom. So half m x dot square, okay, the translational energy of this pulley, of this drum, plus the rotational energy of the drum, so id times omega d square, okay, plus the rotational energy of the pulley, because it will not have any translational energy, so this is half ip theta dot square, plus the translational energy of the 2m mass, half 2m is the mass times y dot square. So again convert all the coordinates in terms of x coordinate. What you will get is half m x dot square plus half, now id is the moment of inertia of the drum, okay. So in case of thin disk, the id can be written as mr square by 2, okay, times omega d. So omega d is nothing but x dot by r, okay, so that is the theta angle, plus half times ip times x dot by rp in this case, square plus half times 2m times y equals to 2x, so this is 2x dot square, okay, so this term over here is 2x dot square, and so this whole thing can be simplified as equals to half 19 over 2m plus ip over r square rp square times x dot square. So finally you can say that this is the T, which is the kinetic energy, and the MEQ is this portion over here. So finally you can say the equivalent mass of the system is equals to 19 over 2m plus IP divided by RP square. This is the equivalent mass of the system shown in the figure. Thank you.